Hi, everybody. You have a nice lunch. We are going to go into a more hands-on working with Jupyter Notebooks portion. Before we do that, I wanted to cover this section because the last notebook is going to need this, and because it also wraps into a lot of what Brian and Sarah have been talking about. And this is about fitting a periodogram. We've already learned about what a periodogram is and the different ways that we can think about it. We might have periodic data, and Brian showed an incredibly similar little cutout of the sinusoid earlier. We might want to fit periodicity. We can make a linear model, as Brian's pointed out, as Sarah's pointed out, which is a periodic function. Sorry, go ahead. You can't hear me? Yeah. Want to yell? I'll try yelling. Okay. Because wait, there's no mic, right? No. Okay. I'll try yelling. If you're hard of hearing, move closer so I don't leave my voice. Periodic sinusoid. It's a combination of signs. The identity that Brian has talked about and Sarah's talked about are that if I want a periodic signal, if I want a sinusoid, I can specify it using three kind of attributes. There's an amplitude, how big is it, how tall? There's a period, how often is it going to come back? And there's a phase, where does it start? Amplitude and phase can both be specified by multiplying the sine and cosine by two factors like this. So if I have a cosine in x and a sine in x, multiply them by some a and b, I'm going to create a new function which has a different amplitude and a different phase. What this means is if I want to create a periodic signal and I want to find the amplitude, find the phase, it's a linear model. All I need is sine of x and cosine of x. The thing though is that you'll have to bake in the period. It is not a linear model in the period. So you have to fix that. Let's have a look at what that looks like. I have created a design matrix. You can see me, like I said, you're going to see me do this particular list comprehension a lot. All I've done is I've said it's a sine and a cosine, and I've stacked them next to each other like this. So it's as many times as I have tall and 2 vectors wide. Then I fit it to my data, and bish bash bosh, there we are. I've now fit on the correct phase. You can see this sinusoid is actually shifted off to one side, and I found the correct amplitude. Right. If we want to create a linear model, we cannot fit for periods. What you could do instead, though, is you could iterate over your nonlinear variables. All I have to do is create my linear model and then just test a lot of different periods and see if any of them are a good fit. Here's another simple sinusoid that I'm plotting. It has a random phase, a random amplitude, and a random period between 1 and 2. If I want to iterate over some trial periods, I can do that very simply in Python. Here you can see what I'm doing is I am iterating through periods between 0.1 and 10 days. It is linearly spaced in frequency, which is the optimal sampling to fit in a periodogram. One of the strictly true. It is an optimal one. And then I'm going to extract the best fitting weights at each of these periods. The weights are 2 across because I have 2 components, sine and cosine. Then all I'm doing is I'm creating my design matrix again, and you can see in here I'm putting in the trial period. So sorry, this has gotten cut off, but you know where I'm going with this. Then I just fit the best fitting weights with our linear algebra solve game. I have 2 weights, and I've done 1,000 period estimates. Now I'm going to say that I want some kind of power. We've already talked about power spectra. We've already talked about FFTs. In this instance, I'm going to say that the power is the square of those weights added together, the summing coefficient, for any of the different periods. There's that periodogram. There's that. What is the power as a function of period? And there's the true period. Great, we found it. Just literally iterated over all of the different periods that we can have. And our linear model has made it so that we can very quickly find the correct amplitude and the correct phase for the best fitting data. Best fitting model. Yes?
So how is this different? Like when we were talking about fitting with systematics, you were talking about that we should be simultaneously fitting everything. So how is, am I jumping ahead? Or
No. Go ahead.
How is this, I guess, philosophically okay in that sense, that to be finding the best fit period and then do systematics fitting for amplifiers?
This is a good question. Let me say the answer. Just a, I'm sure I understand it, so that everybody hears. One thing I wanted to say is, I think you said something like, you have to fit everything into the linear model. Like, you don't have to.
No, simultaneously.
You don't have to fit everything simultaneously, and there are reasons why you wouldn't. What I think your question is if I'm going to iterate over all of these periods and I'm not encompassing any of these systematics, what is the impact of that? The impact of that is could be quite bad. Before, when we had a design matrix, you saw me take one matrix and then start smacking other matrices into it to make it wider, to have more vectors. You can imagine, okay, so I also fit a sinusoid and some systematics, which is what we're about to get to, and then I can do this periodogram. In that way, I can find the best fitting period, allowing for the fact that there's some uncertain systematics that I don't know. Does that answer your question?
Yeah.
You're going to see it in practice in like 3 slides.
Okay, yeah. If it doesn't, I'll ask again.
Okay, good. Ask again if it doesn't answer it. Okay, we've just created a simple classical periodogram. You've actually seen this done a couple of times already. We can rebuild the model to see how well it fits the data. All I'm going to do is say the best fit period is the trial period that had the maximum power. And then I'm going to rebuild my design matrix with that best fitting period, and I'm going to solve to find the best fitting weights. I do understand that I implicitly had the best fitting weights in my previous loop, but then I would have had to do some Python to like get out the correct index, and I thought it would be clearer if we just remade the model. So I have my best fitting period, remake the model. And that's okay. It is not quite correct because we have sampled over a finite number of periods. It's pretty close. If we wanted to be more accurate, we could increase the number of trial periods, or we could do this iteratively and hone in on a trial period until we reach our desired accuracy. Now we're going to try a Kepler data set. It's back again, Kepler 10. You will get so sick of this data set. All right, we are back. We're going to find the best fitting period for this time series now. Now we're going to do our same trick. We're going to iterate over lots of trial periods, and we're going to find the best fitting periodic sinusoid while we allow amplitude and phase to be picked by our linear algebra. Here's our periodogram done in exactly the same way. You can see the best fitting period here is probably around 9 and a few days. We make the model at that period, which we're doing exactly the same way. We get the trial period that's at the maximum power. We make the model using the design matrix. Perfect. Now, already, this is better than our polynomial. Earlier in the day, we were like, why are we using a polynomial? Is this a good model? It might be in some instances where it's just a nuisance and we want to get rid of it. We know stars rotate. We know stars have spots on them. Maybe a sinusoid is something that's better. Sinusoid is something where if I said, what will this look like at time 170, you might actually believe that, yeah, it's probably pretty close. Have a question?
Yes, this period holds for the stellar rotation.
This is the period for the stellar rotation. Absolutely. So you can see here that the wiggle is tracing the sort of stellar variability roughly.
Ask the transit.
No, and in fact, you can see that I didn't mask them here. It is a good question. Should we mask the transit out? Now we're going to come up against the windowing function and aliasing that we've heard all about with these periodograms, because that is in and of itself a periodic signal. I haven't masked them out. I've only given it a range. You can see in this periodogram, which is roughly the range of, I literally eyeballed it and I was like, well, it's between 5 and 10, so we'll just put that. If you started to extend this out to different periods, you would start to see it become confused, or a confusing diagram to interpret. Right, we've iterated over the period, we found a sinusoid. Sweet. There's it. Okay. We can now take this model and we can include other components. Instead of just treating this as only a sum of sinusoids, only a sum of sines and cosines, we can now add in other models that we know to be in the data. Here's an example of this that doesn't talk about planets. Here is a simple sinusoid and a polynomial. I have made a sinusoid that has a random period between 1 and 2, random amplitude, random phase, and then I put in a random polynomial. And it's just a first order polynomial. I know that you can't see me in the data because it's cut off here, but I promise this is a first order polynomial. Now we have two parts of this model. We've got this additive polynomial trend, which I've manufactured. This isn't necessarily real astronomy data. And we have this periodogram that's on top of it. Let's build design matrices to account for this. And we will say, first off, what if it is a sine, a cosine, and just has an offset term to allow the mean to move up and down? A sine, a cosine, and sorry, there's no offset in the first one, then there's an offset in the second one, and then there is an offset x to 0 and a trend into time to the power of 1. Does anybody have any questions when I say that these are the design matrices I'm going to make? The sine, the cosine, sine, the cosine, the column of ones, a sine, the cosine, the column of ones, and a column of time. I know that's a fair amount, but I want you to focus mostly on what's at the bottom. In order, this is a 2-width design matrix with sine of x at a given period, cosine of x at a given period. This one is the same thing with a column of ones, and this one is that with a column of ones and a column of time. And you can see that this is where the period fits best. When we get the true period out and we look at the best fit period in that case where we added that component of the model, we get a pretty good fit to the true period. We can do this now with our Kepler data. We know that the Kepler data is not well modeled by one sinusoid. We can put our planet design matrix back in. We know there's 2 planets, we know the period, we know the T0. We can stack those together and put them back in. We can then iterate over our trial period to get back something like a periodogram. Now we get the periodogram, and this is the period accounting for the fact that there is some transit that has a known period, known T0, but an unknown depth. We stack them all together by doing this V-stack. I found the best fitting period, which is the maximum power. We found the weights, again, just to stop iterating it in Python, just to make it clearer, we found the weights. There's my final fit. You can see now I have a sinusoid with a period that we've been able to iterate and find the best fit period given the explanet transits are in that. If I was to try to fit a sinusoid at a similar period to the explanet transits, it might start to become degenerate. You can see that if I took this to high order, it would start to become degenerate. But right now, they're pretty separate signals at very different periods.
Like zoom into one transit. I mean, I think obviously it will not really fit the transit, but I'm curious how it will look like.
You're about to do a notebook that has all the data, and so you'll be able to zoom in and take a look. It will look like a normal explanet transit with a box right on top of it. Because that's the only model that we get. Okay. Remember, Sarah, we can do higher orders. We can just increase the order of the sinusoids that we're fitting in order to get more flexibility in the signal that we're fitting. If we take this to higher order and we fit our model, this time not only planets, not only a single sinusoid, but now higher order sinusoids, we can still find our periodogram, we iterate over all those periods, find the best period, remake the model, and now it looks like this. I know that this doesn't look dreadfully different, but you can see that this is no longer a sinusoid. This part is much more flat than this part is. This part is much more flat than this part is. This model is saying there is some smooth periodic function, which doesn't have to be a sinusoid. It can be more complicated than a sinusoid, but that function plus some planet function. This is a much better model, a much more motivated model than our silly polynomial. If you ask me, will this look correct out of 170 days? I might actually believe that yes, it would. If you ask me, what will it look like in 1,000 days? I probably wouldn't believe it because there's differential rotation. But this is a fairly interpretable model and something that we can use to both fill in inside this gap if we wanted to interpolate in here, or we could extrapolate outwards and still have some belief that the model is correct. Okay, that is what I wanted to cover before we got onto the workbooks. Does anybody have any questions?
high order case, how do you like truncate the order? It's like not overfitting.
Okay, this is a great question. How do you truncate the order when you're fitting so you don't overfit? Another way to say this, I think, is how do you know that you've made your design matrix not too wide or not too narrow? How do you know when to stop? How many components should you use? This is a great question, and this is where you would have to bring in other statistics to figure out, okay, like criteria, ASC, to say, okay, I have now, adding any more components will overfit. The other thing you might want to consider is your astrophysical knowledge of what is going on. Depending on the signal that you're trying to isolate, you might know that you are only looking for periods that change. You know the size of spots compared to the size of the star, and so you may be able to reason that there's no need to go to like order 1,000 because you're only looking for spots that have variability on timescales of, let's say, half. The last point is you will not be able to fit this model. If I have 200 points in time, you will not be able to fit a model that has more than 200 vectors in it using this system. So there is a limit that you can hit if you want to do linear regression. Does that answer your question? It's okay if it doesn't. If it doesn't, you cannot. And ask more. Your question is answered. Okay, try the notebooks and you just flag me down.
Yeah.
I have more questions. Let's do the first two notebooks. There's a basics notebook, which shouldn't take you very long. This is sort of paint my numbers, fill in the blanks. Then there's a Kepler 10 notebook. The Kepler 10 notebook will go through effectively what we've just looked at and some stuff from earlier. And I will be going around and flagging